Assalamu alaikum. In a previous lecture, we discussed about the different unsymmetrical faults: single line to ground fault, line to line fault, and double line to ground fault. Now we'll discuss the three-phase fault, which is of course the symmetrical fault. We have already actually discussed it, but we'll discuss it as per the symmetrical components. So when the three-phase fault occurs, all the three phases will be short-circuited like this. And in this case, you can see that the boundary conditions will be IA plus IB plus IC will be equal to 0. Three-phase fault is by default a symmetrical fault. And since the three conductors are connected to each other, that means VA will be equal to VB will be equal to VC. So since it's not connected to ground, we cannot say that it will be equal to 0. So in this case, fault current will be same as the phase A current or phase B current or phase C current. It will be, let's say, phase A, IA. So using the symmetrical component matrix IA not IA1 IA2 A times IA, IB and IC, sorry, A inverse times. So separating the sequence currents, IA naught will be equal to 1 by 3 IA plus IB plus IC, that will be equal to 0 because by default symmetrical summation of symmetrical current will be equal to 0. That means this IA naught will be equal to 0. This is an important result for this. And IA1 will be equal to 1 by 3 into IA plus A times IB plus A square times AC, that is, sorry, IC, that is what I have written here. But IC will be equal to A times IA and IB will be equal to A square times IA, which I have written over here. So I will replace IB as A square IA and A, it will be equal to A cube IA, and IC will be A times IA, it will be again A square A cube IA. So I will take IA outside, it will be equal to 1 plus 1 plus 1, that is 3. 3 and 3 will cancel out. This IA1 will be equal to IA. So here fault current will also be equal to IA1. So IA1 here is non-zero. Similarly, to calculate IA2, 1 by 3 IA plus I square IB plus AIC, it is just the expansion of the matrix. We know that this IB is equal to A square IA, A square and A square will be equal to A raised power 4, and this is A square IA, it will be equal to A into A square. A raised power 4 can be written as A cube into A, where A cube is equal to 1, it comes out to be A. So A into IA, A square IA will be taken common, it comes out to be 1 plus A square, which is, if it is 0, then IA2 will also be equal to 0. Now using the voltages, we get the sequence voltage VA1 will be equal to 1 by 3 VA VB plus A square VC. Since VA, VB and VC, they are same, so this can be replaced by VA, this can be replaced by VA, and VA is taken out, so it will be equal to 1 plus A square. This is also equal to 0, VA1. So VA1 can be written as 0, and VA1 we know that is equal to EA minus IA 1 Z1. So IA1 from this will be equal to EA by Z1. So its equivalent circuit will be simply a voltage source that is supplying current to us and impedance of Z1 only. So you can see it, its equivalent circuit will be like this. VA1 will be the voltage across this, and it will of course be equal to 0. So this is the sequence network for the three-phase fault, and which we have actually derived in the symmetrical fault as well, where we have IA is equal to V by Z1. One more important thing is that triple L and LG fault are the same, because you can see there will be no current to the ground when LG fault occurs. It will result the same current irrespective whether the neutral is grounded or not, whether the neutral is involved in the fault or ground is involved in the fault or not, because of the symmetrical nature. So what are the observations from the different faults? Positive sequence currents are present in all types of faults, irrespective of the fault, whether it is symmetrical or unsymmetrical. Positive sequence currents will be present. Negative sequence currents are present in all unsymmetrical faults. Unsymmetrical faults will contain negative sequence current definitely. Positive will be there, negative will also be there in unsymmetrical faults. Zero sequence currents are present when the neutral of the system is grounded and the fault involves the ground. So zero sequence currents are present. First, there are two conditions. First condition is that neutral should be grounded, and in case of fault, ground should be involved, and the neutral current will always be equal to 3 times IA naught. So these are some observations which we actually note during the derivation of different faults. Now we can summarize all these what we have done. So fault type single line to ground for I can be calculated as EA divided by Z1 plus Z2 plus Z0 plus 3 times Zn if it is neutral is connected to ground. And if we have a fault impedance, we may have 3 times Zf as well. So in case of double line fault, we have E divided by Z1 plus Z2 and plus Zf if we have this fault impedance as well. So LLG, its IA1 will be equal to EA divided by Z1 plus Z2 into Z0 plus 3 times Zn divided by Z2 plus Z0 plus 3 times Zn. If Zf is there, here we have to add one more, that is 3 times Zf. Here also we have to add 3 times Zf. So for three-phase fault, whether it is simply three-phase fault or three-phase to ground fault, its IA1 will be equal to EA by Z1. So zero sequence currents will be present in LG fault. Actually, all the sequence current will be present here. So I'll predominantly have more consensus or IA0. In double line fault, IA0 will be absent, but IA1 and IA2 will be present. This double line to ground fault, IA0 will be present. All sequence current will be present. And in case of three-phase fault, this is present, even IA2 would also be present. When this is present, IA0 will be present, IA2 and IA1 will always be present with this. So what is the relation of IF? IF will be equal to 3 times IA1. And in case of this fault, it is root 3 times IA1. And in case of LLG fault, it is IN, which is equal to 3 times IA0. And in case of three-phase fault, it is simply IA or IA1. Relation of IA1 in single line to ground fault, all the sequence currents will be same. In case of double line fault, it is IA1 is equal to minus IA2, and in case of this fault, it will be IA1 plus IA2 plus IA0 will be equal to 0. There must have been one more relation, that is VA1 should be equal to VA2 should be equal to VA0. I have forgotten to write that. You should mention it. And in case of this, IA is equal to IA. IA1 will be equal to IA, that is the fault current, and IA2 and IA0 will be equal to 0. These are the different relations for IA1. One more important, we need to see when the fault occurs at the terminals of a synchronous generator when it is neutrally solidly grounded, what happens to the fault current in case of single line to ground fault and three-phase fault. So we'll compare these two currents, that is what is the amount of fault current when a single line to ground fault occurs and when three-phase fault occurs. Let's first see single line to ground fault when occurs, what is the value of magnitude of the fault current. Fault current is given as 3 times IA1, and in IA1 is equal to EA divided by Z1 plus Z2 plus Z0. Here Z1 is equal to Z2, usually the case in most of the cases. Here Zn is equal to 0 because it is solidly grounded. That means directly grounded by a simple wire. So fault current for a single phase will be 3 times EA divided by 2 times Z1 plus Z0. But Z0 here for a synchronous machine, as we have discussed earlier, is very small as compared to Z1. Now the three-phase fault, IF three-phase will be equal to IA, that is equal to IA1 to be equal to EA by Z1. Multiply numerator and denominator with 3, it will be equal to 3 times EA by 3 times Z1. So IF three-phase will be equal to 3 times EA by 3 times Z1. We will simply compare equation 1 and equation 2. You can see the numerator is same 3 times EA. Here also the numerator is same 3 times EA. Here it is 2 times Z plus Z0, and in the equation 2 it is 3 times Z0. That means this equation has a denominator which is less as compared to this denominator. Because 3Z1 will be greater than 2Z1 plus Z0 because Z0 is very small as compared to Z1. That means the fault current in the single phase will be greater than the fault current in the three phase. So it means in case of a synchronous generator, when the fault occurs, the single line to ground fault results in the more current as compared to the three-phase fault. This is an undesired condition because the frequency of the single line to ground fault is 85%, and we have to make this current lesser than the fault current in case of a three-phase fault, because in that case the frequency of the severe fault will be more. So but we have the provision to make this single line to ground fault lesser as compared to three-phase fault by simply introducing an impedance of Zn in the ground instead of direct grounding. So this can be done simply by connecting the neutral to ground through Zn. So when we do this, our equation will be modified like this. So this has to 3 times, that is IF 3 phase should be greater than IF single phase. So that means EA by Z1 again multiplied by 3. EA by 3 Z1 should be greater than 3 times EA divided by Z1 plus Z2 plus Z0 plus Zn. That means 3 times Z1 should be less than this, because in equality, whatever is true for the numerators, it will be opposite will be true for the denominator. So 3 times Z1 should be less than 2 times Z1 plus Z0 plus 3 times Zn. So take this 2Z1 to this and Z0 to this, it will be equal to Z1 minus Z0 should be less than 3 times Zn. Z0 should be, or Zn should be greater than Z1 minus Z0 divided by 3. This is an important result. So to make the single line to ground fault greater than the three-phase fault, we need to insert an Zn which is greater than Z1 minus Z1 by 3. But in this case, we have assumed that Z1 should be equal to Z2. We'll see that if Z1 and Z2 are different, what will be the relation. So if this is the relation when both are equal, that is Zn should be equal to Z1 minus Z0 divided by 3. So let us try to do a numerical and it will be clear. A 25 MVA 13.2 kVA alternator with solidly grounded neutral has a subtransient reactance Z1 is equal to 0.12 per unit. The negative and the zero sequence reactance are 0.14 per unit and 0.06 per unit respectively. A single line to ground fault occurs at the unloaded terminal. Determine the fault current, find the value of Xn to make IF 3 phase greater than IF single phase. So first we will calculate simply A1, that is EE divided by Z1 plus Z2 plus Z0, that is given as on its own rating 0.12, 0.14, 0.06. It comes out to be 3.125 per unit. So this is the same. So IF is equal to 3 times IA1, that is 3 into 3.125 is equal to 9.375, and base current will be equal to 25, that is the base is this 25 into 10 to the power 3 divided by 12, 13.2 into root 3, that comes out to be 1095 amperes. So IF will be equal to per unit value multiplied by base value, that is 10265, that's 10.265 kiloamperes. So this is the fault current. So to make IF 3 phase greater than IF single phase, EA by Z1 should be greater than 3 times EA Z1 plus Z2 plus Z0 plus 3 times Zn. Here I have done this deliberately. I may have used this relation directly, but here you can see the value of Z1 is 0.12 and the value of Z2 is 0.14. I first derive it for different Z1 and Z2. So again, that means this denominator should be greater than this denominator should be greater than this denominator. So that means Z1 plus Z2 plus Z0 plus 3 times Z1 should be greater than 3 times Z1. This Z1. So 3 times Z1 minus Z1 is equal to 2 times Z1 minus Z2 minus Z0 divided by 3. That is 2 times Z1 minus Z2 minus Z0 divided by 3 should be equal to Zn. By putting the value of this, Z1 is 2 into 0.12 minus 0.14 minus 0.06, it comes out to be 0.04 divided by 3. This is an important result. If Z1 is equal to Z2, it comes out to be again Z1. 2 Z1 minus Z1, that is Z1, Z1 minus Z0 by 3, that is this result. But you can take any one of these depending on what type of question. If Z1 and Z2 are different, then you have to use this. If they are same, you can use this. So Zn should be greater than 0.01334 per unit. I can take it as 0.015, which is definitely greater than this per unit. So by multiplying the base value of the impedance, that is 13.2 square divided by 25, it comes out to be this value. So this value can be used in the neutral of the generator to make the current less in case of single line to ground fault than the three-phase fault. Now we'll continue with some more numericals. Here, same rating alternator with solidly grounded neutral again, and XD dash, that is the XD dash double dash subtransient reactance taken to be positive sequence reactance to be 0.25 per unit. The negative is zero sequence reactance 0.35 and 0.1 per unit respectively. Again, they are different. A single line to ground fault occurs at the terminals of an unloaded alternator. Determine the fault current and line to line voltage. It is slightly different. It is related to the simple question. It is simple. It is not related to the it is related in general to the faults, single line to ground fault. You may use different faults, but here I'm assuming that single line to ground fault in which all the sequence networks are involved. So again, I have drawn the network. This network is simply taken from the actual derivation. So IA1 is equal to EA divided by Z1 plus Z2 plus Z0, which is equal to 1. Because EA were taken to be equal to 1, you can see the voltage at any point taken to be 1 for an unloaded system. Even if we take it equal to 1 for loaded system as well, I have told you earlier, even if it may be different, if the base is different, so we can take it 1 to make the calculations easier. So here it is 0.2, 5.3, 5.1 is 0.7, so I1 is equal to minus J 1.428. So IF is equal to 3 times I1 is equal to minus J 4.285 per unit. IB is equal to 1095 amperes. Actually, I have not calculated it. It is already calculated in the previous example, because previous example the base values were same. So I have taken the IB from the previous example. So IF will be equal to 4685 amperes in actual value. So to calculate the voltages, we first calculate the sequence voltages. VA1 is equal to EA1 minus IA1 Z1. So 1 minus this, it is equal to 0.643. There is no J, there is no minus. It will be simply, if we can write it in terms of polar form, it will be 0.64 the angle of 0. Similarly, VA2 will be equal to minus IA2 Z2 to be equal to this, that is minus 0.44 4998 to be equal to minus 0.449 at angle of 180 degree or minus 180 degrees. Similarly, VA naught will be equal to minus 0.1428. VA is equal to 0. This is just for the checking for this. You can see this is 49. This is 14, 49 plus 14, 63, almost equal to this. When we take these two all into account, it comes out to be equal to 0. This is for check. Because VA, we are considering VA is connected to ground, so that it will be equal to 0. Now VB1 will be equal to A square VA1. We have calculated this VA1. We multiply 1 angle 120, it comes out to be this. You just put the value in the calculator, you will get this answer. Similarly, VB2 is equal to 8 times VA2. So put the value of VA2, it comes out to be 0.25 minus J 0.433 per unit. VB0 will be equal to same, which we have already earlier calculated. Similarly, we can calculate VC1, that is 8 times VA1, VC2 is square times VA2. This is the actual value for this, and VC0 will be same as VB0 or VA0. Phase voltages, VA0 will be 0, VA will be 0, we don't have to calculate it. VB is equal to VB1 plus VB2 plus VB1 plus VB2 plus VB0. So VB1 plus VB2 plus VB0, when you add these three voltages, sequence voltage, you will get this VB. This is value is this. Similarly, VC will be VC1 plus VC2 plus VC0. Add these voltages, we get this. This is the VC value. Now VAB will be equal to VA minus VB. Since VA is 0, it will be simply minus VB. So it will become minus 0.2143. VBC is equal to VB minus VC. You can see it from here. VB minus VC. These two values are same. This and this will cancel out. This one, this will be added. Minus this, minus it will be minus 1.9796 per unit. Similarly, VCA will be equal to simply VC, because VA is equal to 0. This is V. So calculating the magnitude wise VAB, that's the magnitude of this, it will be equal to 1.0127 multiplied with the base value, that is 13.2. It comes out to be 13.367 kilovolts. Similarly, VBC is equal to this multiplied with the base value, it comes out to 26.13 kV. Or VCA is equal to VC, and VC is simply this, its value, its magnitude is 1.027. So when multiplied, it comes out to be 13.367. So this is how you can calculate different phase voltages, different line voltages after the fault occurs. So let us try to do one more numerical. Actually, this is the numerical which relates the system when the system is loaded, not unloaded. So in this case, I try to include both the parts, that is the theoretical part as well as the numerical part, because I haven't shown you the loaded system, and earlier also when we use the loaded system, we usually use the Thevenin theorem in that case. So we'll do the same thing. So let us first read the question. The question reads like this: a 30 MVA 13.8 kV three-phase alternator has a subtransient reactance of 15% and negative and zero sequence reactance of 15% and 5% respectively. It means alternator has 0.15 per unit positive reactance and 0.15 is same negative reactance, negative sequence reactance. And zero sequence reactance is very small. The alternator supplies two motors over a transmission line having a transformer at both the ends as shown in the single line diagram. That will come in the next page. The motors have a rated input of 20 MVA, 10 MVA, both 12.5 kV with 20% subtransient reactance and negative and zero sequence reactance 20% and 5% respectively. So motor rating is, one motor is rated as 20 MVA, 12.5 kV with positive sequence reactance 20%, negative sequence reactance same as 20% and zero sequence reactance as 5%. The second motor is 10 MVA, 12.5 kV, positive sequence reactance 20%, negative sequence reactance 20% with zero sequence reactance as 5%. Current limiting reactors of 2 ohms each are in the neutral of the alternator and the large motor that has shown like this. Current limiting reactors are connected between neutral and ground. The three-phase transformers are both rated 35 MVA, 13.2 on delta side and 115 on Y side kV with leakage reactance of 10%. So the rating for them are same. Series reactance of the line is 80 ohm. The Z0 for the line is 200 ohm. Series reactance is 80 ohm. Determine the fault current when LG fault occurs or LL fault occurs and LLG fault occurs at point P, that's at point D. Assume VF, that is the pre-fault voltage, to be 100. This is actually 120 kV. This is not 1120, this is 100 kV. Let us first decide what are the different voltage in the different zones, because these transformers will change the zone of the base of the voltage. So take base as 30 MVA and 13.8 kV on the generator side. Actually this is the base of the, this is the MVA rating of the generator itself. So we'll take this as a base. So base kV is the secondary of the T1 and the primary of T1, that is in this we'll calculate, that is this zone, we'll calculate base, that is 13.8 in the transformer ratio. Transformer ratio is, you can see, 15 by 13.2, 115 by 13.2. So it comes out to be 120 kilovolt. It is fortunately equal to the pre-fault voltage. We can take this pre-fault voltage to be 1 per unit in case of the fault. Base voltage on the motor side, it will be 120, that is this, multiplied by 13.2 divided by 115. This is 13.8. Here also we have a base kV as 13.2. So we have calculated the base kV on the different sides, different zones of the power system. So here I have shown that this Y is connected through reactance, that is current limiting reactor, whose value is 2 ohms. Here also its value is 2 ohms. Now coming back to the scene, we'll first make the positive sequence network. We'll first calculate, because calculation of this is not to be done. We have taken the base as the generator rating. So the reactance is given for the generator will be same, they will not be changed. So we'll first calculate XT1, it will be same as XT2 because the rating is same. Then XTL and XM1 or XM2 will calculate these values one by one. XT1 will be, its value is given 10% on 35 MVA, but here we have taken the base as this 30 MVA and it is given as 13.2, but we have taken the base as 13.8. So it is 0.1 into 30 by 35 into 13.2, there is 13.8 whole square. It comes out to be 0.0784 per unit. That is also equal to the XT2, because whose XT2 has the same rating as that of this XT1. So XM1, that's the motor rating. Its value is given as 20% at 20 MVA, but our MVA is 30 and voltage is 13.8. Its voltage is 12.5. So changing the base value for our base value, it comes out to be 0.246. Since similarly XM2 will be equal to 0.4922, X transmission line will be 80 into 30 divided by 120 ka whole square, because in transmission line we have 120 as a base kV. It comes out to be 0.1667 per unit. So drawing the positive sequence network, it is same as the reactance diagram as we have done earlier. So this is the generator, this is the generator reactance, which we have not calculated, is given on its own base, and we have taken the same base. This is transformer T1, J0.0784. This is the point P at which the fault occurs. We have to take, this is the transmission line J0.01667. This is the transformer 2, it has the same value, and this is the motor M2, whose rating is less, it's 10 MVA. This is the motor M1, whose rating is more. So since we know that this is the positive sequence network, negative sequence network will be same in uh, identical as that of positive sequence networks here, because here all the positive sequence reactants are same as that of the negative sequence reactant. It will be identical except a voltage source. So you can see I have written the identical values of the reactances, only we have shorted the voltage source. This is a negative sequence network. Now zero sequence network, we have to calculate its reactance individually. First we'll calculate xn. Xn value has 2 ohm on generator side and motor side. And motor side we have 13.8 kV as the base. So divided by the base value, it comes out to be 0.315 per unit. So usually our circuit contains not xn, it is 3 times xn. So it comes out to be 0.945. Xg is same as 0.05, that is 5%. Xt1 is same because in case of Xt1, it is given as leakage reactance. So for transformer, x1 is equal to x2 is equal to x2 is equal to xl, that is the leakage reactance. Here leakage reactance is taken to be the same for the zero sequence network as well. So transmission line is given as the zero sequence reactance is given as 200 ohms. So converting it to the per unit value, it is 0.4167. So for motor, it is changed like this, and for motor 2 it is changed like this. So when we draw it, it will be drawn like this. Generator 1 is connected to ground through a reactance, so we have a reactance 3xn in series with it is Z0 to be the generator reactance. Here the transformer is connected at delta y. You can see delta y. So here it will be delta, and y is connected to ground directly solid. So here you can see this is actually S1 is open circuited, and this is the S2 is closed. S3 is again closed, and S4 is open circuited here. This is same applies to transformer T2. In this case, S1 is closed, but S4 is also closed. S2 is open and S3 is open. So the circuit will be like this. So here, this is the generator, sorry, motor M1, because motor M1 contains X 3 times Xn and its own 0.615, and motor M2, since M2 you can see the neutral is not connected to ground, it is shown open circuit. You can see motor is not connected to the ground, it is then open circuit. This is the zero sequence network of the power system given. Now all the networks are in our hand. Now we'll assume that an LG fault occurs between point this and this. That means all the circuits should be connected in series like this. So when these are connected like this, then we have to calculate XTH between these 2 points, that will be equal to XTH1. XTH between these two, that will be equal to XTH2, that is the Thevenin negative sequence reactance. This will be Thevenin positive sequence reactance. This will be Thevenin zero sequence reactance. First we'll calculate Thevenin positive sequence reactance. So I have taken this circuit out, and I will calculate XTH at between these 2 points. First, these two will be parallel, it comes out to be 0.164. These two will be in series, it comes out to be 0.2451, and these two will be in series, it comes out to be 0.2284. Then these two will be in series, it will be equal to 0.4094, and this is as it is. Then finally these two will be in parallel. So finally XTH1, that is the Thevenin positive sequence impedance, will be equal to 0.1465. And since these values are identical for the negative sequence reactance, and we have to calculate between the same points the Thevenin reactance, XTH1 will be equal to XTH2, that will be equal to J 0.1467. Please don't forget to write this J, because when you are asked to find the magnitude, then you can drop this J. Now for zero sequence network, these two are we have to calculate XTH not between these 2 points. You can see for this will not come into picture, this and this will not come into picture, because they are open. Here only what will come into picture, that is these two will be in series, then this series combination will be in parallel with this. So I have make it a simpler series combination 0.4951. This is as it is 0.0745. Then the parallel combination of these two, it comes out to be 0.067667. So finally it can be reduced to this network, actual zero sequence network. This is XTH1, this is source, this is XTH2, this is XTH3, and the voltage and currents are related like this. Then IA1 will be equal to EA divided by XTH1 plus XTH2 plus XTH0. It comes out to be minus G 2.78. IF, there's a fault current is 3 times IA1, that is minus 8.34 per unit. IB can be calculated like this: 30 into 10 to the power 3 divided by 13.8 into root 3, that is 144.3 amperes. So IF will be equal to 1203 amperes. Similarly, now it is very simple because we have calculated the Thevenin network. It is simple. We can calculate XTH, sorry, line to line for this circuit becomes like this: EA, XTH, IA1 and XTH2. IA1 will be equal to EA divided by XTH1 plus XTH2. So since they are equal, it will be 2 times J 0.1465. So IA1 will be equal to minus G 3.42 per unit. IF is equal to minus G root 3 IA1. So minus, because J into J will be minus into minus will be plus, and J into J will be minus 1. So minus root 3 into 3.42, that is minus over here. This is the actual value 5.923 per unit. So the fault current magnitude will be 5.932 into 144.3, that is 854.7 amperes. We can calculate this triple line to ground fault. This is homework. I will see this in the interaction class. So I'll stop here. I hope all this is understood to you. Thank you.